So in the last lesson, we looked at frequency distributions for qualitative data. In this lesson, we're going to look at frequency distributions for quantitative data. And our goal is to construct some of these frequency distributions, construct some histograms, and then look at different shapes of histograms. Okay, so let's get into the first example here. Suppose we measure the height in inches of a random sample of 40 college students and obtain the following data set. So we get this data set. These are their heights in inches. How do we create a frequency distribution for this data? This is the question, right? How do we create it? This is quantitative data, so there are no natural categories. Remember, when we were dealing with qualitative data, that was categories. And in the example in the last video, we had Nike, Converse, Adidas, right? And we can easily assign each of those a frequency. In this case, there are no categories. It's just a bunch of numbers. How exactly can we break this up? And what we're going to do is we're going to divide it into what we call classes, okay? And this is sometimes called bins. You may hear it called that. In the textbook we're referring to, they use classes, so that's what I'm going to call it for some consistency. So we divide up the data into what we call classes, and this is what allows us to create a frequency distribution. These classes are intervals of equal width that cover all the values that are observed. For this data set, we could choose the classes to be 64 to 64.9, 65 to 65.9, 66 to 66.9, and so forth. So we choose these classes. Us as the statistician or the researcher, we choose these classes. We then count the number of observations that fall into each class to obtain the class frequency. So let's look at this first class that we've created here, 64 to 64.9. There is only one observation that falls in that class, so the frequency for this class is going to be 1. Let's look at the next class, 65 to 65.9. This time there are 2 data values that fall within this range, so the frequency for this class is going to be 2. We could continue this process for each class. We can count up the number of observations that fall within that class. And once we do that, what we obtain is the frequency distribution, which we're going to go down to right now. This is the frequency distribution. We have all the classes listed out, and we have the frequency for each class. The question here is, how did we know when to stop? Well, this was the biggest data value, right? So if I were to continue going, all of these would just be 0, 0, 0, 0. So we just stop once we reach the biggest, okay? So again, this example, we chose these classes. We didn't have to choose them that way, and we're going to get to that actually in just a second. So now let's talk about some important vocabulary. The lower class limit of a class is the smallest value that can appear in that class, okay? So for the first class, the lower class limit is 64 because that's the smallest value that can appear in it. For this second class, it is 65. For this third class, it is 66. And in general, for each class, the lower class limit is this left-hand number here, okay? We also have upper class limit. It's very similar, but it's the upper limit. It's the largest value that can appear in that class. So the largest value that could appear in this first class is 64.9. For the second, it's 65.9, and etc. And in general, the upper class limit for each class is this right-hand number, whereas the lower class limit is this left-hand number. One more thing, class width. This is the difference between consecutive lower class limits, okay? So consecutive means next to each other. So we can pick 1 and 2, 5 and 6. We could pick any two. I'm going to pick 1 and 2 just to make it easy, but it works with any of them. So let's look at the lower class limit. So we have 2 consecutive lower class limits here, and let's take the difference. 65 minus 64, that's 1. Okay, so that's the class width is 1, and that would work with any 2 consecutive lower limits. Notice the difference between all of these is 1, and that's because the way we set up our classes is that they're all equal width. So if we did it right, this should work. We should be able to use any 2 consecutive lower class limits. So that's the class width, and it should be kind of intuitive that there is this width of 1 here, right? So quick knowledge check, going back to the last video. Can you add a relative frequency column to the previous frequency distribution? Okay, so relative frequency, remember what that is? We take the frequency and we divide it by the total. Okay, so the relative frequency for this class is 1 over 40. For this class, it's 2/40, and we can, convert those to a decimal. We can write them as percentages. We can do all that. But I just wanted to give a quick reminder and review because that is something you'll still be asked to do, is find relative frequency. So in the frequency distribution we just looked at, remember the classes didn't have to be exactly how they were. We chose those classes. We could have chose them to be different. And that's what we're going to look at in this practice example right here. And I put a star here because I really like this question. I think it's a good exercise, and I'll probably put it on an exam. So I'm just giving you a little heads up. So we're going to construct a new frequency distribution using the same data set, but this time using a class width of 1.5. We're also using 64 as the lower class limit of the first class. That's actually the same as the previous frequency distribution. The only thing we're changing is this class width. Instead of 1, it's now 1.5. So really the question is, given a class width and the lower class limit of the first class, can you construct all of the classes? That's what we're going to practice right now. So let's see if we can do it. First, we're going to start with this piece of information here. 64.0 is the lower class limit of the first class, because what that tells us is that this number right here is 64.0, okay? What else do I know? Well, I know the class width is 1.5. How can I use that? Well, I can use that because I know that the difference between any two consecutive lower class limits is the class width, which is 1.5, which means whatever this second lower class limit is, the difference between it and 64 must be 1.5. Another way to say that is this second lower class limit is 1.5 bigger than 64. So let's add 1.5 to 64. And that's how we're going to get this lower class limit. And remember, this works for any two consecutive lower class limits. So we can just continue this process to get all of these lower class limits. The only thing we have to keep in mind is, how do we know when to stop? That's the question. Well, we stop when we reach a lower class limit that is bigger than all of the values in our data set. So let's look at the largest value in our data set. That's 73.4, which is easy to point out because they're all nicely ordered for us. It won't always be like that. So 73.4. So that's going to fall within this class, right? Because this upper class limit is going to be less than this for sure, okay? So this class here is going to have 0, and every class past that is going to have 0 as well, which tells us that we don't need it, okay? So all of these classes here will be able to capture all of the data values we have in our data set. So now we just need to find these upper limits. How can we find these upper class limits? Well, we can notice that 65.5 here, that means that this upper class limit is going to be 65.4, right? Because we want our classes to fully cover all of the possible data values. So we don't want there to be any gaps. Okay, so 65.4 falls into this class, then 65.5 falls into this class. There's no possible data values in between, right? Because we're rounding to the 10th place, of course. So we can do the same thing. We can look at this number and subtract 0.1 to get this number, or we can look at this number and add 1.5 to get to the next upper class limit, because we know that that class width works for consecutive lower class limits and consecutive upper class limits. So either way you want to do it, I tend to like to look at this and subtract 0.1, which means that this is 66.9, and that this is 68.4, and that this is 69.9, and that this is 71.4, and this is 72.9. And then from here, there's nothing bigger to look at, so we can just add 1.5 to this, if you want to remember that. 74.4. All of these classes are the same width. They all fully cover all of the data values, so we're good to go. Now we just need to count up the frequency for each class. So 64.0 to 65.4. How many of these heights fall within this interval? 1, just one, because this is bigger, right? That's going to be in the next class. So just one, frequency of 1 for this first class. 65.5 to 66.9. 1, 2, 3, 4, 5. So a frequency of 5. 67.0 to 68.4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's a lot of data values in this class. 68.5 to 69.9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 again. So this class has a frequency of 12. Now let's look at 70.0 to 71.4. 1, 2, 3, 4, 5. Just 5, right? These 5. Frequency of this class is 5. 71.5 to 72.9. 1, 2, 3, 4. And then there's going to be 1 in that last class. So we have 4, 1. So again, this is something I expect you to be able to do. You'll have plenty of time to practice it in the homework and also on the quiz. But I think a good exam question would be to give you a data set, give you a class width, give you a lower class limit of a first class, have you construct the frequency distribution, and then have you construct a histogram for that frequency distribution, which is exactly what we're going to do next. So once we have a frequency distribution for a set of quantitative data, we can put the information in graphical form by constructing a histogram. So remember when we had qualitative data, we constructed bar graphs. Well, for quantitative data, we can't do a bar graph because it's quantitative. What we can instead do is a histogram, and it's kind of similar in the sense that they both involve rectangles, but still pretty different. So let's see if we can practice. A histogram is constructed by drawing a rectangle for each class. The heights of the rectangles are equal to the frequencies. So that's actually the same as a bar graph, right? The heights of the rectangles are equal to the frequencies. But this time the widths are equal to the class width. The left edge of each rectangle corresponds to the lower class limit, and the right edge touches the left edge of the next rectangle. I think the best way to make sense of all this is really to look at an example, and you're going to practice these on your own in the homework and hopefully get familiar and comfortable with them. So let's look at this first frequency distribution we made, the very first one we made where the class width was 1, okay? So let's construct a histogram, and I already did it, so I'm going to show it here and explain exactly how I constructed it. So I first started with the vertical and the horizontal axis. I labeled the vertical axis by looking at this range of frequencies here. I noticed that 1 was the smallest and 9 was the biggest, so I marked it all the way up to 10. That way I can spread everything out. For this horizontal axis, I looked at the lower class limits. Okay, so along the horizontal axis, we always label it using these lower class limits. You notice that here, 64, 65, 66. And then this last number here is what would be the lower class limit of the next class if there were one, right? We typically use that to cap it off at 74, right? So where do the heights of these rectangles come from? Well, those come from the frequencies. So this first rectangle corresponds to the first class, and its height corresponds to the frequency of that class. So the height is 1. So let's look at the first class, 64 to 64.9. The frequency is 1. Then we have a frequency of 2 and then of 3. So let's make sure that lines up. 2 and then of 3, right? So the frequencies correspond to the heights of these rectangles, where the widths corresponds to the class width, right? The width of each rectangle is 1, which is the class width. So just a quick recap. The vertical axis, we label it with the frequencies. The horizontal axis, we label it with the classes, but really we use the lower class limits, right? Then in between those labels, in between those lower class limits, we have rectangles. The height of each rectangle corresponds to the frequency of that class, and the width corresponds to the class width. So the last thing we're going to discuss is the fact that different histograms have different shapes. It turns out that this is one of the purposes of creating a histogram, is to see the visual shape of a data set. So statisticians have developed terminology to describe some of the commonly observed shapes, and that's what we're going to look at right now, these new vocabulary words. So a histogram is symmetric if its right half is a mirror image of its left half. Very few histograms are perfectly symmetric, but many are approximately symmetric. So actually the example that we just looked at of the data with the heights, it's not perfectly symmetric. The left half is not a perfect mirror image of the right half, but it's pretty close. I would say this is approximately symmetric, right? Another example I have is down here, this middle histogram here, approximately symmetric. Compared to these, we're going to talk about right now, a histogram is skewed to the right if it has a long right-hand tail. So that's this guy here, skewed to the right because it has this long right-hand tail. Whereas a histogram is skewed to the left if it has a long left-hand tail, like this. Okay? So there's one more thing we're going to talk about, which is mode, because it turns out that all of the histograms we've looked at so far have been what we call unimodal. Okay? So let's figure out what that means. A peak or a high point of a histogram is referred to as a mode. A histogram is unimodal if it has only one mode. So let's look at all these high points. So here is a peak or a high point. That's what we refer to as the mode. This histogram has one mode. Same here, peak or high point. So this is the mode. This histogram has one mode, so it's unimodal. Same with this one. Same with the one we drew. So here's an example of one that is bimodal. This has two clearly distinct modes here and here, two peaks or high points, right? So this is an example of a histogram that we would call bimodal. Hopefully this was helpful. If you still have any questions, if you need any help, anything at all, send me an email. We'll hop on Zoom and get it figured out. Hope all of you have a great rest of your week and a great weekend, and I look forward to being back in person on Monday. I'm excited, so I hope you all are too, and I will see you then.